Hi everyone, I hope that you're doing well. In this lecture, I want to discuss the theory for one sample proportion procedures, and we'll actually see a return of the z-distribution here, which is really interesting. We'll do a review of the basic theory first. We'll start with tests and confidence intervals. We'll go over a test example, then a confidence interval example, and discuss some odds and ends. Then we'll go over procedures for two sample tests for a difference in proportions. Again, those are z-distributed. We'll go over a test example, CI example. I wanted to start with a little bit of review though. So I've been over this many times before, but it never hurts to emphasize, I think, that fundamentally what we're doing here is the same. It's been the same for the last few lectures. We're basically looking for some kind of sample statistic, whether that's a mean or a difference in means or a proportion or difference in proportions. We're subtracting off from it the mean of a sampling distribution under the null, and then we are dividing out by the standard deviation of that sampling distribution, or the standard error. So what we're doing today is, basically what we've been doing for Z and T procedures. We'll see that regression works in basically just the same way. Chi-square tests are a bit of an exception, but we'll get to those soon. In every case, though, what we're doing, we've got a sample statistic. It's drawn from a sampling distribution with a known function, and we standardize by subtracting the mean under the null and then dividing out by the standard deviation. Here, the standard deviation will change a little bit depending on whether we're doing a test or a confidence interval, because of some reasons that are interesting and a little bit not worth summarizing now, because I'll discuss them in just a moment. So the general confidence interval recipe won't change. Just reminding you what you do. You pick a level of confidence. You find out the number of standard deviations from the mean, whose area under the curve is C. You multiply this critical value, which you can denote z star or z sub d, by the standard error. In this case, here I just wrote sigma over root n, but it won't always be that. This is just kind of the general recipe. And then you add and subtract the resulting number, the margin of error, to the estimate to get a range of plausible values. Hypothesis tests, you basically write down a null hypothesis, an alternative, and an alpha, a cutoff p-value. You picture the sampling distribution. If H naught, your null hypothesis, is true. Then you compute the test statistic. Generically, it's this here, but sometimes that'll differ a little bit, right? Because we'll sometimes have differences in what the sample statistic is and what the population parameter is and the standard error, but this is how it looks generically. Then we find the probability of data this weird or weirder. The alternative hypothesis tells us where to look, so we might look in one tail at the other, or both. And then we compare this p-value to alpha, which is a cutoff p-value. If it's below alpha, we reject the null, and we say that we have statistically significant results. If it's above alpha, we fail to reject. And here's a handy slide. Again, I produced this in the last set of slides, but here you can see it one more time. So at the end of today's lecture, we'll actually know how to do all of these things here. We're not going to worry about these +4 modifications, by the way, just a heads up. So let's dive into the new material. So what are proportions? Well, formally they're a statement that two ratios are equal. So A over B equals X over Y is a proportion. So saying that 4 over 5 is equal to 16 over 20 is a proportion. Usually what it means is something expressed as a decimal or as a percent. So A over B is equal to K over 100. A over B is K percent. So a simple example, when we say that the proportion of unionized workers in the US is about 9%, this is a slightly inexact way of saying that the ratio union workers to all workers is equal to 9 over 100. We care about proportions for obvious reasons. So anything that can be expressed as a percent can be treated as a proportion, from the percent of people who plan to vote for a policy to the percent of people who are married or those who suffer cancer. These are all proportions. This background here isn't super necessary for understanding what follows, but I just wanted to remind you because it's good to define terms. So inference on proportions is very similar to inference on means. Recall that proportions are the mean of a collection of dummy variables, d1, d2, dn. And this requires us to recall that we can think about every person in a sample as the realization of an independent and identically distributed random variable, meaning that if we replace people once we sample them, unlikely, or we have a giant sample and taking one person out of the population doesn't really change the population much, which is true for the US, right? If I select one person for a sample, or even 10,000 people for a sample, and then I take another person, I haven't practically changed the US population since it's in the 300s of millions of people. can't remember the exact number now. It's well above 300 million. So taking out 10,000 people isn't going to do very much at all. So when that's true, what that means is that we've got basically individuals in the sample who are all realizations of some random variable. And in this case, when we're thinking about dummy variables, I'll use an example now that I'll use throughout the lecture, whether or not someone is married. That means that we basically are pulling someone and seeing whether they have a 0 or a 1 on this variable. Status of being not married, 0, or status of being married, 1. And when we say that people are identically distributed, what that means is that these random variables, before we actually grab someone, so when we're thinking about, to use a metaphor that my colleague David Scallender, who's currently a TA in this course, uses, and I really like it, imagine a roulette wheel that's still spinning, right? So a roulette wheel is something you might see in a casino. You don't have to be super into gambling. You've probably seen it in a movie before. It's a big wheel that a casino attendant spins and then it stops spinning at some point. Or you can think about it maybe even more colloquially as when you're rolling a die, and sometimes people really like to, roll it a few times just to really put the luck into it. So when someone is rolling, like they're kind of juggling it in their hand, that die is still a random variable, or rather the upward face is a random variable. But once it comes to a rest, it's a realization thereof. So what that means is that before we actually pick someone into the sample, say we want a sample of size 1,000, so we say we're going to have 1,000 people in there. But before we actually pick them, they're all random variables, and they're all drawn from essentially the same distribution. Again, with a slight, and in most cases, totally imperceptible difference, because once we pluck one person out, technically we change the underlying population. Basically, those are identically distributed, and they're independent because picking one person doesn't affect who else is picked. And that's true even if we change the underlying population a bit, because it still doesn't mean that there's any particular logic between the value of one person and the value of another. Okay, so proportions are kind of almost halfway between counts, which are binomially distributed, and means, which are Z or T distributed. And by the way, why can we not just treat this as an extension of the binomial distribution, for instance? Because that seems awfully similar to the binomial. The problem is that the binomial is a discrete distribution. It's got a limited set of values, 0 through n for k, or x in some denotations, where x is the random variable, meaning the number of successes, and then we use k to mean some specific number. Technically speaking, best practice would be to use big X for the random variable, little x for the realization, but people tend to find that confusing. That can't take on non-integer values, but a proportion can. So that's why they're different. So what's different with two sample and one sample t-test for means then? Because that sounds a lot like a mean. We know that the proportion is the mean of a dummy variable, or its probability of a success. Well, the standard error formula changes because proportions have a specific simple formula for their standard deviation. It turns out that can be expressed actually as a function of the mean. And even further, hypothesis tests and confidence intervals each use slightly different formulae for the standard error for basically a similar reason. And interestingly enough, also for this reason, proportions are approximately Z-distributed, which is pretty cool. So let's look at the central limit theorem in action for proportions. So just like the count of successes in a sample, the proportion, or the count divided by n, is approximately normally distributed. Here's another simulation using the CPS as the population and subsamples thereof for the replication. So on the left, we've got the marital status for all Springfield workers. And then on the right, we've got the proportion married to Springfield workers in 500 samples, each of size n equal to 1,000. Note here that on the left, we've got this nice fact that the mean of this population level distribution is equal to 0.5254, and that's also equal to the probability of someone being married. It's just 0.5254. That's a nice fact about the mean of a dummy variable, and that's why we use this kind of pair of Greek letters here. The mean mu always means the mean, but in this case it also can be expressed simply as the probability of a success. And we've got the variance here as well. Remember that the variance of a dummy variable is super simple to calculate. It's just pi times 1 minus pi, and the reason for that is that we learned early on, although this is a bit of advanced knowledge, but the variance of a dummy variable, or the variance of any variable really, can be expressed as the expectation of the square of the variable minus the expectation of the variable squared. So if you think about the square of a dummy, you square everyone's value on it, everyone's got a 0 or a 1, basically does nothing because 0 squared is 0, 1 squared is 1. So that would give you the expectation of the dummy, which is pi. And then you've got the expectation of the dummy then squared, and that's just going to be pi squared. You have pi minus pi squared. That can be expressed as pi times 1 minus pi with a bit of algebra. So that's a very nice fact about the variance of a dummy variable. Then if we think about the variance of a collection of n dummy variables, we basically want the variance of the sum of dummy variables divided by n. We can pull out a constant from the variance. We just have to remember to square it. So we pull out an n squared. And then we've basically got n times the variance of one of the dummies. So n times pi times 1 minus pi. Then you cancel out one of the n's and you have pi times 1 minus pi over n for the variance of the mean of a dummy, or in other words, the proportion. So sigma squared here is going to be pi times 1 minus pi over n. And that happens to be in this case. Well, we already found this here, so we would just divide this by n equal to 1,000, and you can see that we're just shifting over the 2 by 3 spots here. The mean, maybe more intuitively, is actually very similar here to the mean. The reason for that is that this is not the true sampling distribution. It's just a fairly large simulation, although not even that large, just 500 samples here. 500 replications. Now remember, in practice, you don't do these replications. You don't need to. The sample size you care about is this one. It's that each of these is a mean of 1,000 people. That's more what you care about. Okay, very cool. And again, note that these are not exactly what theory says they should be, but here I just did this simulation and I took the empirical values here and they're basically equivalent. So that's good news. So here's some facts about the sampling distribution that I kind of just said out loud and showed, but the sampling distribution of a proportion is actually normal. It's not t-distributed. That's because the variance of sample proportions, like that of counts, is fully specified by the mean. So for a given n, it's just a function of one random variable, the population probability, which is again represented with pi. So we don't actually have to worry about this ratio of random variables business that we have with sample means. There's only one random variable here. It's just instead of also the sample standard deviation, it's just the mean. So that's good news. We again estimate the standard error by plugging in our sample estimates. So the mean of a proportion across many samples is going to be pi. So the variance of a proportion across many samples is pi times 1 minus pi over n. And the root of the sampling variance, which is the standard error, is equal to the root of pi times 1 minus pi over n. And in this case, I'll often just use the variance because it doesn't require writing this out. And also it's very hard, maybe impossible, to get this to extend. So this should extend over the whole thing, but for simplicity, I'll just sometimes write it without the need for a radical sign here. And you'll see this is actually a bit of an oversimplification actually. We'll estimate the standard error in different ways depending on the context of the problem. That's one thing that makes proportions a little bit tricky. I'll probably fix this slightly in the actual presentation since this is a bit of an oversimplification. So let's get into those details. Hypothesis tests for proportions are basically the same in general. We set up the null and the alternative, calculate the test statistic, compare it to a critical value or get the exact p-value with software, and then we conclude. The test statistic is going to be familiar in the abstract. It's the sample statistic minus the postulated parameter over the standard error. But the standard error, since it's fully determined by the value of the parameter, is given by the null hypothesis value for a test statistic. And you may want to take a look at the notes here. So note that the standard error for a mean and a proportion are actually very similar, and the variance for a mean, it's just the variance formula as we know it. But for a proportion, it's what we saw in the last set of slides, and I kind of gave this proof out loud. But the point is that the quantity in the standard error is just the proportion itself. So if we're thinking about picturing the sampling distribution under the null hypothesis, we need to use the standard error that is actually given to us by the null value, because that's how we do a hypothesis test. We picture the sampling distribution under the null, and then we check and see how weird our results would be given that. So we're actually going to use the null hypothesis value in the standard error calculation. But otherwise, this is the sample proportion, or the sample guess at the probability, minus the estimate, or the guessed population proportion, or null hypothesis value, over the standard error. So this isn't changing at all. Confidence intervals are also generically very similar. We decide a level of confidence and an associated critical value. We calculate the sample statistic, the standard error, and the margin of error. Then we add and subtract the margin of error. But since we don't have any particular null in mind when we calculate the CI can be used to test values, but that's not its primary purpose, and it's not required in the way that it's required with the hypothesis test. We're just going to use the observed or sample proportion when calculating the standard error. So here we just use pi hat and 1 minus pi hat. Note that these two will be similar if our null hypothesis value is close to what we use, and the difference will grow as our null hypothesis value gets farther and farther from the observed one. Just something to note. So let's look at an example. We're going to dive right in. So let's consider a case where we're interested to test that in the GSS 2018, in the US 2018, because we're making a claim about the population, of course, the proportion of people who think that the state should not help pay for medical care is about 15%, or exactly. And then the alternative will be that this proportion is not equal to 15. We'll do a two-tailed test. Let's say that a score of 4 or 5 satisfies the condition thinks the state should not help. Let's change alpha a little bit for fun. How about 0.01? And you'll see that the syntax of the proportion test in Stata requires you to set up a dummy variable. So even though we can do this by hand without needing to make a dummy variable, what we're really doing by hand is making a dummy variable. We're just not doing code. But you should do that if you need to in Stata, and I'll show how to do that. First, we'll do it by hand, though. So this is the formula for our test statistic again. The observed proportion, which is this here, is, if you recall, we had these people here, so 1.29 and 117. We're going to ignore the missings, by the way. And then we're going to divide that by the sum of everyone. So this is the sum of everyone. These are the other three values, and we get a proportion of 0.1610. And I probably should have put this first, but now you can see that it agrees. We just did a little bit of calculation by hand. Then, of course, we only have a couple more things to compute. We're going to compute, quote unquote, the null hypothesis value. Just plug in 0.15. Then we need to compute the standard error under the null. So we'll do that now. So we've got 0.1610 minus 0.15 on top. And then we're going to have 0.15 times 1 minus 0.15 or 0.85 over 1528. That was our sample size. We get a z-score of 1.20. And note that we can find an exact p-value easily in Stata, but we can use table C for a decision if we want to. So let's do that now. Note that in table C, we actually have this z row as well and that's not a pun on zero, by the way, this is just the row for the z where we don't have degrees of freedom. So basically, we could have been using this the whole time. Why were we using table A then? Well, it is actually best to report exact p-values. But here we can see we're between these two here. So our two-sided p-value is between 0.2 and 0.3. Admittedly, we're close to the cutoff for a one-sided test for alpha of 0.1, which is what we were using just for the sake of variety. But here we're doing a two-tailed test, and also we don't get to cheat and just say, well, we're pretty close. Again, the whole logic of accept reject is a little silly and arbitrary in the first place. It's best to report p-values, but a lot of times this is what people do in practice, so you should just know that that's what people are up to. The difference here is that we could use table A, and indeed I think that would be the best option. So here, remember how table A works, these are standard normal cumulative proportions or probabilities, so we get left-sided p-value of 0.8849, but we're going to find the p-value associated with the tail, so that's 1 less that value, and then we're going to double it for a two-tailed test, obtaining 0.2302. In other words, under the null hypothesis, we'd see results this extreme or more about 23% of the time. That's not weird enough to trigger rejection for most people, so we're going to fail to reject. This is what this looks like, and you should always be drawing these things here. So this is the unstandardized sampling distribution under H0, and we've got our sample proportion here. So this is 0.161. This is the null hypothesis value, and then this is the right tail p-value I was just describing verbally. This is the left tail. And then these are our critical values here. I didn't draw in the rejection region this time, but this is the critical value. Again, there's a variety of different ways to draw stuff like this. This is just what I did. An important stated note about proportions. So PR test and CI prop only accept dummy variables. It's not the case in general that proportion tests only work on dummy variables. However, you can work by hand or use the command proportion. Remember that dummy variables are simply those that take on only two values, 0 and 1, which we use to represent absence and presence respectively as some property, which we typically use for the name of the variable. So Protestant, for instance, should be coded so that 1 are people who are Protestants and 0s are people who are not. That's convenient, of course, for numerical purposes because it gives these nominal variables a basic quantitative character. And one advantage that I foreshadowed actually a couple of months ago now, it's been a while, is that Stata requires dummy variables for at least some proportion procedures. There's some, plenty of sample code about this in DAP1 and the lecture as well. So let's see how we could do this in Stata. And I'm actually going to transition here and show you how to make this dummy variable. So the syntax is quite simple, right? It's this syntax here. PR test variable equals, and you can write double equals. Sometimes Stata is nice and doesn't force you to do that. So let's start a fresh Stata session. Whoops, here. I need to probably go in and save my code from when I was working. Yeah, I do. One nice and not so nice thing about Stata is that it's extremely fussy. So about saving stuff. So actually, if you try to quit Stata without saving all your work, actually, at least on this type of operating system I'm running here and this MacBook, and this is pretty general, this is just a fun Stata side note, if you try to quit and you've got unsaved changes, not only will it not do it, but then you actually have to go in, hand save, and then force quit the program. It's just really fussy about that, as it probably should be. But anyways, so let's paste in this code. And by the way, I always put code in these lecture notes so you can see what I'm doing. So we're going to use our relevant data set here. We're going to use the GSS 2018. I need to put a change directory command in here myself. So get to my directory here where this works. Then we'll use the GSS. So let's look at this variable. This is our help sick variable. And we see here, in this case, the code book gives us the value label. It doesn't always, so we don't need to go through the rigmarole here of using the value label. We could find that in this way. So we would just see here that we've got this label. You could also get it from describe like this. So, and then we could say label list. And we get this here. Note that there's two unlabeled values, which is quite interesting, but we're not going to do much about that here. So let's make a new variable like this. We can say gen public health equals dot. This is the empty shell. Then we're going to replace public health equal to 1 if help sick is less than 6 and greater than 3 and not missing. So we'll do that here. And you can see that we've made 246 real changes. And what that represents then is basically taking the sum of these two groups here and assigning them to this new value equal to 1. The label public health, by the way, is not really the best label here. We probably should use a different one, but that's just what I used, and I'm not going to go change all the slides. Probably this should be something like health individualism, something like that. Then we'll make public health equal to 0 if help sick is less than 4 and not missing. Remember that this not missing is important because Stata will evaluate, like usually it just ignores missing values, which is what you would want it to do. It's the good default behavior. But technically speaking, it internally represents them as arbitrarily large constants. And what that means is that sometimes if you have these unbounded statements, like replace public health if help sick is greater than 3 and you don't do anything else, that's why I put this in here, by the way. This is kind of overkill, but that's why it's in here. In fact, we could just change this out and we could just say this here. I'll show that this produces the same exact results. Probably should update the code. Oops. And you can see it makes the same number of changes. So then we can do the same thing. We can replace public health equal to 0 if help sick is less than 4 and not missing. Again, this is extraneous here, but because it's not going to create an error, but it's a good thing to do generally. Another thing you can do is just basically drop people that are missing and then just don't save the data. That's typically a good idea as well. Then we can go ahead and look at our new variable here. And it looks like this has worked correctly. So we wanted to send people to 0. who in some respect support, some amount of like social healthcare. And then we've got people who are ones who, generally speaking, are pro, individual responsibility, quote unquote here. Then we can make a value label. I kind of made a funny value label here just for the sake of it, but we do this like this. By the way, one utility that I haven't shown very much is this. We can also label the variable, which is often helpful. So label variable, we'll say public health, and then we'll say R's opinion on state spending, state, let's say, paying for healthcare. And then we can tab this again. And you can see that this is a little bit more informative now. Then we could do our proportion test. So we'll come here, we'll say PR test public health equals 0.15. And you can see that we get the same rules that we got before, and we get basically the same answer that we got here. Note that we need to tolerate a certain amount of rounding error. So here we had 0.2302, but you can tell that's because we rounded our test statistic a little bit. We get 1.2036 here. And note that we could find this in Stata, right? This is another alternative. So we would first find the value in the tail. That's what this step does here, and then double it, and we should get the same thing as Stata. And we get 0.22874, which rounds to exactly this. So that's how we would do that there. Again, you don't really have to do that bit in Stata. You don't have to reproduce this probability here. I'm just showing that if you found a probability by hand, then you could compute it in Stata in this way. There's very many ways to solve a lot of these problems, and you just sort of have to use a bit of common sense and your intuition. Part of this is a learning process. Okay, so this is what we saw before. Coming back ahead here. By the way, this reproduces my Stata annotated output from before. I'm not going to review that in detail. There's quite a long discussion of that in the t-test lectures, so go see that if you want. There's actually less to focus on in our output here because, for instance, we don't have degrees of freedom. It is worthwhile to make sure you understand these probabilities here. Note that p lowercase p here means the population proportion, which we're using pi to refer to, and that's because it's a little bit less confusing than just having an uppercase p. Stata uses PR actually very likely for that exact reason, that it wants to eschew any kind of confusion here. Okay, very cool. So there is that. So let's move right along. I guess I'll make maybe one more comment here too. You can see Stata calculates the standard error for us. That's the standard error that we found by hand. We got the same t statistic or z statistic, pardon me. And the confidence interval we'll come back to. It's actually a little bit of an interesting challenge to calculate. So why is it a bit of a challenge? Well, it's because the formula changes a little bit. Because we're not actually testing a specific value of the parameter here, we're just going to use our best guess at what that value might be, which will be the sample proportion or the sample estimate of the probability. So here's our original variable, here's our new dummy variable. How could we calculate this? So what we would do, oh sorry, I did this out of order here. The very last. Let's fix that now. This is highly frustrating. Sorry about that, folks. So this is our formula here. What we're going to do is take 0.1610 and then subtract from it 1.96, our critical value for a 95% confidence interval. And then in this case, by the way, we were using this alternative alpha, so we really should use like a 90% CI. But I want to show that we can reproduce Stata's default output here, so we're going to use the 95%, which is their default, as it is for most software. So we have 1.96 times the square root of the estimated probability in the sample, 0.839, and we again found that by just taking this 246 divided by this here. Hopefully that's intuitive, kind of basic arithmetic for everyone. Then we multiply by 0.161 here, that's this quantity, and then divide by n, and then we do the same thing, but we add rather than subtract the margin of error, and we get 0.1426, 0.1794, and we can see that this is the same thing as what we get either when we just do the confidence interval for proportion on the variable and we add the option walled. Walled just tells Stata to calculate the standard error in the way that we've done. or it'll be close to the same thing that we get in this default output here. You don't necessarily, well, let's say for this class, you should generally speaking run a separate confidence interval, because I can't remember exactly what exact formula for the standard error is used here. There's different ways to do it. We're just picking one that's quite simple and theoretically kind of elegant. So I would recommend doing CI prop and then the variable, and adding the walled option, but in general, the standard error calculation won't be that different. Okay, so that's that. Note that this method also works in Stata if you don't want to convert to a dummy and don't want to calculate it by hand. You can see some sample code for more details. Here you have to specify the CI type. In this case, we're going to use the option normal. And what this does is, if you were just interested in one of these values here, for instance, that the strong position that the government should help or the state should help, not lumping 2 or 3 together, then you would just use this command here, prop, and then help sick, and then comma CI type normal. This is an abbreviation of proportion, by the way. And note that it gives you all of these things here, so it'll do it for every category. You're allowed to do that, although there's some tricky business here. So in general, it's not a bad idea to convert to a dummy variable when you're doing this, especially because when you do 2 group tests for a difference in proportions, you'll typically speaking need to focus on just 2 values of each, or else you'll end up doing a chi-square test, which we'll discuss next week. Some odds and ends. There is this +4 modification. Our book mentions this. There's no need to use it. It's actually a bit of an oversimplification of what's called the Agresti-Cool interval. There's some details on that in the footnotes. I'm not going to get into that. I did want to mention that it's easy to implement in Stata by using the option Agresti. That's just the name of the person that came up with this. Since the book doesn't tell you that that's the name of the modification, that's a small pet peeve of mine about our book, is that while I think it's a good idea to avoid the kind of great man theory of history and focus on like giving certain procedures the names of people, Agresti is actually still alive. He's a current statistician, at least as far as I know. He might have passed recently, but he's was around recently. But on the other hand, there's something that's a little bit annoying when introductory textbooks like hide things from readers by not even mentioning the name of a procedure, or not even mentioning the name of an advanced textbook where you could learn about this. On the one hand, it does keep things simple, but on the other hand, it means that it can be difficult to use other sources besides your textbook, because the textbook doesn't, an advanced user, such as myself, without meaning to put a feather in my cap, can immediately see, oh, this is what they're doing. They're just calling it something different, but it can be really aggravating for neophytes to encounter procedures that sound very similar, maybe to things they've seen elsewhere, or maybe they don't, but the person is just like, where can I learn more about this? And then the textbook, for fear of throwing too much jargon at you, fails to tell you that this is actually something that's got a name that you could research. So that's something I don't really like about our book. You don't need to use the simplification when working by hand, and it rarely makes a difference, and it's really necessary with the kind of data that we have. One point about the book, too, I'm just going to give the book a real lashing here. Our book is generally not so great about deciding when to include more advanced material or not. I found that when it includes more advanced material, it often does it at points where it doesn't really seem that necessary, and sometimes it fails to introduce things that are a little bit more advanced, but are really strictly necessary. So I don't really love how they're keen to include kind of random odds and ends here and there, but then to leave out certain glimpses at advanced material that might be quite useful. Okay, so that's my spiel on that. Let's talk about 2 sample proportion procedures, then we'll wrap up. So the big idea is this. The general logics for the hypothesis test and confidence interval are the same. The only things that change are the raw statistic and the standard error. In this large simulation of the sampling distribution on the right, we see here the simulated difference in true proportions for the marital status of all Springfield workers by race. So you can see here that for non-white individuals, the population probability of being married was 0.4469 with rounding. For whites, it was 0.5611 with rounding, and the difference was 0.1142 with rounding. And then the variance on the right interestingly, is the sum of the true sampling variances for each group. So we could find that here. I'll show you that in the footnotes. So you can see here we have 0.4469 times 1 minus 0.4469 divided by 500. Each of these are size 500. And then we have the same thing for the other group here. So 0.5531 times 1 minus, that should be 0.5531 divided by 500. And if we pop this in, we can just put this into Google here. We get 0.00098, and then with rounding, you'll see that's pretty close to what we get here. There's a bit of a difference, again, that just comes from the fact that we don't have the true sampling distribution here. We just have a simulation thereof. But basically, we'll use that fact in just a moment, that the variance of this sampling distribution is closely related to the variance of each of these two underlying variables here, the mean for the non-white group and the mean for the white group, or rather the actual variable itself for each group. So those treating those as separate random variables, and then treating their means as separate random variables. And the mean of the sampling distribution here is also the mean of the difference here. So all of that is really nice because it sort of fits our intuition. It doesn't differ from what we would expect from basically our lecture on differences in means. So there's a parallel difference here, however. If we calculate a confidence interval, we're going to use the observed difference in proportions. So what that means is that we'll assume that they are in fact different, and we won't do anything kind of special beyond that. If we do a hypothesis test, we're going to pool the sample standard deviations because we assume that there is no difference between the two groups. And so in this case, we don't have a null hypothesis value for the actual, what we're saying, the null hypothesis deals with the difference between the two groups. So we're saying that we assume that their probabilities are the same, but we're not also saying that they're equal to some specific value or not. A little bit confusing. So what we're going to do is just let that come from the data. So unfortunately, that's not even exactly a parallel difference. So we really have 4 separate formulae here that we have to keep track of. Here they are. So for hypothesis tests, let's actually start with confidence intervals. So this formula for the standard error is exactly what we would expect from basically considering the means, both random variables that are uncorrelated. So the, across different samples, we're not going to expect there to be any correlation between the mean of the white marital status dummy and the mean of the non-white marital status dummy. If we happen to get a sample that's weird, that happens to have a lot of non-white people who are married, there's not any reason to suspect that whites in the same sample are going to be, kind of weird on their sampling distribution. Those means are uncorrelated. We would only expect them to be correlated if we had a matched pairs design, but these are not matched pairs designs. If we were doing something like neighbors or interracial marriages or something like that, then it would be the case. But that's those things are just much more specific than anything I possibly could have mentioned. So in general, you'll kind of know when you have matched pairs designs because it'll sound like people in the sample were paired in some way. Okay, so then what we do, we just have the variance of a sum of random variables. So we just add up their variances, and then we take the root to get the standard error. Pretty straightforward. The sample statistic here is just the difference in observed means or proportions, same thing. And we just take that sample, we add and subtract to it our critical value. Basically, we have a sampling distribution for the difference in probabilities or proportions that is normal, and it's centered on the true difference. And so really all the stuff we learned with single sample groups is exactly the same. Okay, what about hypothesis tests? Well, we've got this standardized value here that we need to calculate. Again, we've got this difference in means at the top. Now, we don't actually have this option, or at least it's not as easy with proportions to have a non-zero null. So I'm not including the null hypothesis value here, which would be simply pi1 minus pi2 or pi1 naught minus pi2 naught, because it actually gets a little bit complicated for reasons that I discuss in the footnotes. Actually, sorry, right here. Because again, the variance of a proportion is fully determined by it. So we're not going to deal with that. Again, one nice thing about differences in means or proportions is that the null is much more intuitive. It's usually pretty reasonable to assume that it might be 0 for a given group. So then what's all this business here? Well, what we're doing here is we're going to use as an estimate of the variance of each group the pooled variance because, or the variance from everyone, because if the two groups are the same, then they would have the same variance. Because it's fully determined by the value of the proportion or the parameter here. So note that when we multiply this through, this is just a simplified way of writing this basically over this group times this here over this group. And the proportion is going to be the same, but the variance will depend also, like the sampling variance also depends on the sample size. So we basically get an estimate of the variance of the dummy, which is independent of sample size, and then to turn that into a sampling variance of a group of people for a proportion, we just divide out by the relevant sample sizes. So we multiply through in that way and then take the root. Hopefully, the book doesn't present any of this logic whatsoever. It just tells you that these are what are true. It's a little bit frustrating to me that they put, again, this would be like going a little bit into the algebra of variance would be such a better idea than going into like the +4 modification and stuff like that. But, that's kind of I guess what you could say is we have a book that's very non-mathematical in a lot of ways, but also is very keen on providing people with like the absolute latest up-to-date, kind of kludges and tips and tricks. And I just think what that results in is a book that's quite detailed and in many ways very messy, but not in a way where it's actually pushing you to really learn a lot about the math. So I do think it's kind of a worst of both worlds situation. And actually earlier editions of this book used to be better about that, some of that stuff, but so be it. So anyways, these are the two formulae. The key thing to understand, right, is that in both cases, we've got fundamentally the same procedure here. So in this case, we've got a sample statistic, the observed difference in proportions or means of dummies, estimated from the sample, minus the null hypothesis, which is here 0, divided by the correct form of the standard error. That's what you can think about this as being, is this is the correct form of the standard error in this particular case, if you want to simplify it. The same is true for the confidence interval. So we have a observed difference. This is our observed sample statistic, plus or minus the critical value, same as always. This part isn't going to change at all from when we first learned confidence intervals, actually. So for 95 CI, it's just 1.96. For 90 CI, it's just 1.645. That part doesn't change at all. And then we multiply by, again, this is the correct form of the standard error here. That's how you should think about this. So I'm going to go ahead and give an example now. Your TAs are going to go over this with you in your labs if you're in my class this semester, since we simply won't have time for this. I'm actually out next Wednesday, and so also these examples involve a fair amount of like somewhat tedious calculation. So I wanted to just present these now, but we're not going to have time to go over these in lecture. But I'll describe this for the future. So last year, it's actually a couple years ago, this is a COVID-era experiment. An example, a massive study conducted in Bangladesh was heralded as sort of the debate ender about the theory that face masks work to control the spread of respiratory disease. Sorry, some typos in there. Masks work, the authors say. And we previously, not actually in this version of the course, since we had not enough time to cover this, but in the fall 2022 version, we discussed some experimental design issues with this study. You can see those here. One of the key issues was that there are what are called Hawthorne effects, or in other words, basically subjects, when they're aware that they're being perceived, oftentimes will change their behavior. The name refers to a classic study done at a plant of this name. Basically, it's kind of an interesting fact. Workers basically did better under apparently all experimental conditions. Like the researchers couldn't find a single thing that actually caused the workers to do worse, which was kind of surprising. And then they just basically figured out, oh, it's us being here. They feel like we're gonna, tattle on them to the bosses, so that's why they're doing better. Better, quote unquote. They're being more productive, more exploited. Okay, so that's one of the issues, is that in this study, basically, since it appears, since people knew whether they were assigned to treatment or control, that people assigned to the treatment group decided to maybe there's at least some speculation here that there was an incentive, or people in that treatment group understood that they were not supposed to be getting sick, quote unquote. And since there was not actually random testing of people for the presence of COVID, this caused a problem. Let's set that aside, though, and let's just look at kind of the math. So Ben Resch, who's a professor of computer science at UCLA, writes a really interesting blog, wrote a useful summary and critique, which extracts the main results from their belatedly published raw data. The study is super long, so it's nice to just get the raw data, and they actually didn't include it. So even though it's over 100 pages, they didn't actually include the raw data, which is a bit of a strange thing. But it turns out you can do a simple two-sample proportion test on those data. We'll see a caveat about this later. But here's what's exciting. Scientists conducting studies that have huge effects on public health policy are roughly doing stuff that you know how to do. So let's try to get those same numbers that Professor Resch obtains. His Python notebook is here. Python is a kind of all-purpose programming software, which you can also do a lot of data science stuff in through the what's called the sort of pandas package. A couple really good books on that are Wes McKinney's book, Python for Data Analysis, and Jake Vanderplas's book, The Python Data Science Handbook, if you're interested in either of those. I just literally have those right on my desk now, and I'm looking at them. Those are how I learned Python, so I recommend those. So basically, here's the setup. So in the randomized controlled trial, there were basically this many cases. I'm not going to say these long numbers out loud. You can copy them down. This was the control N, this was the treatment N, and then we had the basically number of symptomatic individuals, which you can treat as successes here. Again, success is one of those terms that's kind of weird because it's like, is it really a success to get sick? But here we just need to assign one group to basically be the ones on the dummy, and it typically makes the most sense to pick the group that is like more notable. So having COVID would be more notable here. More notable like relative to some context, basically. So our number of successes for the control is 1106, number for the treatment is 1086, and the proportions would be this divided by this, and then this divided by this. Again, hopefully it's obvious how to do that. It's a pretty small raw difference in cases here. So, not a huge number. You can note here that these are just different by 20. But one kind of useful thing about the math, or one cool thing about the math, is we can check and see, well, is this actually a statistically significant difference? So here is our formula for the test statistic. So we're going to take that observed difference in proportions for, this can either be the treatment or the control group, it doesn't matter. Generally speaking, it makes the most sense to calculate a positive test statistic if you can, for the sake of kind of making the math a little bit more intuitive. So since more people were infected in the control group, and that's how also the researchers did it, or at least Professor Resch did it, we're going to make them group one. So this will be control, this will be treatment, and then we'll take the pooled proportion and in the sample, and then we'll multiply it by the sum of the sample sizes. And again, don't think about it as summing these two, then multiplying. Think about it as multiplying this through to get the estimated variance of our dummy, then multiply that by 1 over n1, and then 1 over n2, and then we add them because that's the formula for the basically sum, the variance of a sum or a difference of two random variables that are uncorrelated here, sample means or proportions. Okay, so now it's just plug and chug. Now this part's going to be a little tricky because there's a lot of plug and chug. So we first find the sample proportion here for the control, then the treatment, and that turns out to be this number, which is very, very small. So we need to be careful. By the way, generally speaking, the normal approximation for the sampling distribution works poorly when proportions are close to 1 or 0, which means that we should probably look a little bit askance at this. Actually, neither Professor Resch nor the researchers mentioned this, but it's a kind of a big deal. So just a word to the wise. Then our pooled proportion is this here. So now we just add up the number of cases positive total over the sample size total. We get this number here that's quite similar. Then we find 1 minus pi hat here, or in some notations q, if this is denoted p or q hat. That's this quantity here. We're going to need that to estimate the standard error. So then we estimate basically the variance of the dummy overall, which is this quantity here. and then we turn that into sampling variances by multiplying through. I'm not going to write these out because these numbers actually get extremely small, so it's best to avoid rounding them, period. We basically get the formula for the z-statistic like this. We take our difference, we pop it down here, then we can just directly, without needing to round, multiply that estimate of the dummy variance here by the sum of the sample sizes, and we get a number that's actually like surprisingly not huge or tiny. It's 2.42. So that's a z-statistic that's of a size that we actually know how to handle. If we go ahead then and get the exact two-sided p-value from Stata, it's 0.0157, although we could also just look this up in table A. So we actually have some evidence against the null of no difference for most levels of alpha, although not all. For instance, not 0.01. That's consistent with the main claim of the study that masks reduce symptomatic infections in communities with higher usage. But there's still some very large problems of experimental design with this approach. So it's an unblinded study. There were non-random seroprevalence draws, which means people's blood was drawn. The proportions are extremely near to zero, and given the very small effect size, it's just 20 people in villages of hundreds of thousands of people, we should be a little bit careful about this. Also, moreover, as Professor Resch notes, we should be careful here about using a method that presumes simple random sampling, so that both groups of people who were tested for antibodies were plucked randomly from the sample population, with a study design that necessarily, given that the claim is that masks work on a group level, was sampled randomly from within clusters. So we shouldn't actually use this simple two-sample z-test here, but Professor Resch shows how to do it, and I thought it might be kind of a nice way to show you that the stuff matters. What's the actual conclusion about the study, by the way? We can't really say much. The sample design is just actually not too great. By the way, here's how you could check your work in Stata. You can use the immediate form of a proportion test, which has this syntax, PR test I, then the number of observations in group 1, the probability in the sample in group 1, and then the same for group 2. I find it easier to avoid rounding, to basically just write out the kind of sizes here. You can do this in a couple of different ways. You could write these locals here as the props. So local prop 1, that puts it in a variable, and then you can invoke that variable later in the syntax. You can also, and I thought I put this in here, actually just write out the ends as well. So you could say local n1 equals whatever, and then pop it in just like that. And you can see that we'll get the same answer. So let's show this in Stata. And fortunately, what this does is also give us, we can do this in a couple of ways. One, you can just run each of these separately, which is not too bad here. So we'll run this, we'll run this, we'll run this. And you can see that we get the same p-value, same z-statistic here. By the way, locals work in two ways. I think I've mentioned this at times in this lecture series before, and certainly in my project tutorials. Locals only work in a given kind of like space of Stata. If you're doing this in a do file, a frustrating thing is once you run a particular block of code, the local disappears, which is intended behavior, but it can be frustrating at an intro level. When you're working interactively, the local persists. So I can say di prop1 here, and it'll still show it to me. So sometimes if you're working in a command window and just playing around with stuff, like you want to just quickly check out the results, using locals is fine like that. Okay, so let's go ahead and proceed to another mask study to do a confidence interval for proportions. So another controversial RCT on the effectiveness of face masks for wearers was released recently. This is actually now 2020, but again, I like these examples, so I'm going to keep using them. Based on research done by Danish epidemiologists. Once again, we looked at this study during our experimental week and said that it had some significant problems. So I was just bashing the pro-mask study. Let's bash the anti-mask study. One thing that's not so great about this is that it was not actually testing whether or not masks protect other people from infection. It was testing whether masks protect wearers from infection, which is not typically the claim made by most mask advocates. You can verify that if you look at the experimental design here. So here are the author's key data. What was their 95% confidence interval? Can we reproduce it? So here you can see basically we've got our ends in this case, and then we need to find the rates of infection, so they give those to us here, 42 in the mask group, 53 in the control group. But does that mean that the masks were more effective? Because we do have lower rate of infection in the mask group, and then one that's higher in the control group. Let's check it out. So here's our formula for the confidence interval. So first we'll find the estimated probability in the sample of, in this case, we're going to use the mass group first, just to be consistent with the authors. So we have 42 divided by 2392 is this. Then we do the same for the unmasked group, which is this here. And note that with rounding, we get the same results as the authors here. They seem to do something a little bit funny with this rounding here, because 53 divided by 2470, you can see here, we can just briefly verify that, is, I think they rounded a little bit oddly. Yeah, 2.1. We would actually round this to 2.1. That's what sorry, never mind. I'm forgetting the details here. I just rounded here to 4 places. So we're consistent with the authors, because if they rounded to just 2 places, they would get a different answer. Okay, so we find our difference in groups here. So we take this less this to give us the raw sample statistic. So in the sample, mass squaring was associated with a 0.3 percentage point decrease in infections. And by the way, a brief note on percentages versus percentage points. There's different reasons to use one or the other depending on the context. Percent always implies that you are comparing one raw thing to some kind of like baseline, so typically the sample size or something like that. Percentage points are a little bit different. So I think I gave an example on the slides here. Yeah, so here's a concrete example. I'm not going to make one up off the top of my head. If you're thinking about, for instance, me shooting free throws from the free throw line, I shoot about 60%, and Shaq, God bless him, one of the greatest ball players of all time, but terrible free throw shooter. He shot about 53%. So I am 7 percentage points better than him, but I'm actually 13% better than him, because 60 less 53 over 53 is that. There's some debate about whether you should use percentages of percentages. In other words, taking a percent difference of percentage points. Some people would argue that there's nothing wrong with that. Other people would argue that that's suspect in some cases. Fortunately, in this case, we don't really have to worry about that, because literally what our procedure tests is a raw difference in percentages, i.e. a percentage point difference. So we don't have to worry about that here, unless we were using a more advanced method. So then how do we calculate our lower bound here? Well, basically what we're going to do is take the raw statistic less the critical value. Authors did a 95 CI, so we'll do the same, 1.96 times the square root of, get ready, take a deep breath, the probability for group 1, and here I just, and basically again, we're using this observed difference, right? So this is just the variance of the sum of these variables here. 0.0716, or the difference, by the way, it's the same for this difference and the sum of two random variables. So 0.0176 times 1 less that, divided by 2392, plus 0.0215 times 1 less that, divided by 2470. Take the root of the whole thing, and we get negative 0.0117. Or in other words, again, since we make group 1 the mass group, it could be the case that negative 1.2 percentage points, or in other words, the mass group did better by about 1.2 percentage points, but here it comes. What's the upper bound? So this is actually 0.0039 or 0.4 percentage points. What? Yes, it is true. So our confidence interval includes 0, and it goes further, and it actually even includes the possibility that the mass group actually did worse, and that this is just sampling noise. In other words, it's a really noisy sample. Again, we're pretty close to 0 and 1 with our estimated probabilities and their complements. The probabilities are near to 0, the complements are near to 1. Observed here, for instance, this is very close to 1, this complement here, or Q hat in some notations. So what that means is we should be, again, skeptical of the experimental design and of the applicability here, but with rounding we're able to get the same answer as the authors, which is very cool. And the idea is that, yeah, technically speaking, this result is highly inconclusive. It doesn't actually demonstrate what we might think it does at face value, which is that the mass group did better. So pretty interesting stuff. Thanks everyone for watching, and I hope you have enjoyed this lecture on 1 and 2 sample proportion tests and confidence intervals.